of the people in the industry are using reaction wheels because they are easier to use. But for many reasons, we have started developing miniaturized control moment gyroscopes. So CMGs usually that's a very large actuators. For instance, on the International Space Station, they don't use reaction wheels; they use
Okay.
CMGs.
Well,
Um,
let's get into it then. So, what is the difference between reaction wheels and CMGs? Why would you choose one or the other? What are the situations that make
um,
it relevant?
so a reaction wheel, it's simply like turning a wheel in one direction or the other, so accelerating a wheel, that's how you would generate torque. But a control moment gyroscope, it's having a wheel mostly at a constant speed. And then, as a child, usually you always make the experiment of holding a bicycle wheel and then trying to turn it. And then you actually realize very quickly that there is an opposing force that is generated to you. Um, and that's what we use with CMG, which is a much more power efficient way of generating torque on the satellite. The
Okay.
reason why it's not widely used, it's because the control laws. So combining different CMGs into a system and then having laws to control it, it's much more complex. Um, it's also generating what you call singularities, which is a state with your satellite where for a certain vector you cannot input directly that command. You feel a bit blocked, and that's why usually people don't really like CMGs. Uh, but our technology is kind of a hybrid solution between reaction wheels and CMGs. So we can accelerate or decelerate our wheel, whereas like for traditional CMGs, you are always at constant speed and you cannot change the speed of the wheel. But we
Okay.
can do that. So that means that we can actually operate our wheel as a reaction wheel if we want to, and that allows us to go around the singularity. So
Okay.
in the end, our control laws become much simpler, and our solution takes the advantages of reaction wheels and takes the advantages of CMG into some kind of a in-between solution. And that's what we have developed for nano satellite at first, because as a Taiwanese company, um, well, there are no shortcuts. Usually, you need to use nanosatellite. You need to use CubeSat to demonstrate your technology, to show that it's working, to show that it's flight proven. But we are now offering more and more products for small satellites that are above 100 kilograms, even 400 kilograms. So we have a project with the Taiwan Space Agency to demonstrate our much larger the CMG in space. So even if we started with nano satellites, we think that there is a real market for our solutions for much larger platforms with remote sensing payload, for instance. And then that opens really a new market where you're able to um, turn your satellite to point your satellite into different direction much faster. So you're able on one orbit to target a much wider range of targets compared to satellites which have only reaction wheels as actuators.
Okay. So
Um,
let's go back a little bit. Actually, could you introduce
yeah,
yourself, introduce the
sure.
company,
Yeah, sorry.
maybe explain when the company started and what problems are you solving?
So my name is Julien Hennequin. I'm head of sales for TensorTech, which is a Taiwanese company that has been, I think, started in 2020. So it's still a quite young company. As of now, we are 30 people working for TensorTech, and we think that we are ADCS experts. So we don't only manufacture hardware. We also provide the algorithm, we provide the full solution, with actuators, sensors, we are able to do simulations for our customers, so to evaluate the performance of our system on their platform and determine what the best configuration for their satellite is with our hardware. And on top of this, we can also provide testing equipment. So we have a ADCS test bed where we can do full hardware in the loop testing. Whereas most of I would say a lot of people now just do software in the loop testing, but we're able to go beyond that and to do hardware in the loop. And that's something that differentiates us from, I think, some of our competitors. Whatever we deliver is tested on our own ADCS test bed as a full hardware in the loop
Okay.
system.
And did the company emerge because of a specific project or a specific mission into space, or was there just problems in the market that you saw needed to be solved?
Um, to be completely honest, the co-founder of TensorTech started the company not necessarily having space applications in mind. They were actually, I think my colleague and the CEO of TensorTech told me that he was watching the movie, I think that's iRobot, where you have Will Smith, I think, riding a motorbike, which is having wheels working independently and like turning in very weird ways. And that really convinced him to start working on this kind of technology. So
Hmm.
he was really aiming for this kind of applications at first, and this kind of technology use what you call spherical motor. And spherical motor is really the technological key enabler for what we are doing. So whereas a traditional CMG is using two small motors, we are actually only using one, which are coils surrounding a wheel with a permanent magnet inside. And so we are inducing the movement. Uh, it's not generated by a small motor in the axis of the wheel.
Okay.
And the original project was to even have a reaction sphere, so a sphere that you would be able to control on three different axes. Um, that's not there yet, mostly because um, you need to have some kind of lock mechanism when you launch on a rocket. Otherwise, the sphere in the middle of the system is starting to act as a pinball. It's going to be very difficult to maintain the integrity of the system. So they went back to, I would say, a bit simpler system. And they realized that there were a lot of different applications for space, and CMG was one of them.
Okay. And so with these CMGs, I mean, you mentioned earlier you can do nano satellites up to much bigger satellites, or
Mhm.
you're aiming for this. Is it a technology that is applicable to any space project, or are there certain conditions that are best suited for this kind of CMG device?
It could be used for any kind of satellites or space applications, but I would say that the ones that are going to benefit the most from it are the like remote sensing, so that you can point in different directions with great agility while still keeping your power budget pretty low. Um, the other one is um, everything which requires maneuvers, for instance, for space debris, for in-orbit servicing, uh, where you need to have long maneuvers, um, so requiring additional momentum storage, which is the capacity of a system to um, make a maneuver without reaching saturation point, which is where you reach the maximum speed of your wheel, and then you need to um, reduce the speed of your wheel while compensating with your torquers. And that's a situation which sometimes can completely abort a maneuver when you reach that point. So if you are aiming for long, complex maneuver that sometimes in orbit servicing requires with robotic arms and so on. That's where our system is also very, very interesting. So that's I would say the two applications that it's really, really benefiting from our technology.
Okay. And what are the trade-offs that people might need to be aware of? Are there any weight concerns people should be aware of, or anything like this that's worth mentioning?
Well, it's actually a quite compact system, very power efficient. So if you do a swap analysis, I think we are also very interesting compared to traditional CMGs for sure, but also reaction wheels. Reaction wheels at some point needs to be very large, very heavy to provide us like additional torque. And that's where CMGs are, for instance, used on the International Space Station is like it's because beyond the critical size, critical mass, it doesn't make sense to use reaction wheels anymore because the power consumption and the mass is too large. So that's where also we can be I would say providing additional value to certain missions where it's not necessarily the agility which is important. It's not necessarily the mountain storage, but it's more like the power consumption, for instance. And it's kind of two sides of the same coin where yes, for the same amount of power, we can provide more torque, but it's also like for a given torque, we are also using less power, and that's one aspect that for some business application, it's actually more interesting.
Okay. Can you talk us through maybe a recent innovation or development or evolution of a certain feature or aspect of one of your products, and talk us maybe through the history, something that's particularly relevant or pertinent now or exciting?
Sure. Well, first of all, we started with this whole new technology. I was also very happy to work for this Taiwanese company because I think they were a bit of the stereotype of Taiwanese companies sometimes like just copying, not necessarily innovating in space. And I think that's really not the case with TensorTech, and that's really a company leading innovation in Asia. Um, we have developed other components like sun sensors, magnet talkers, control board, etc. So we are more and more developing all the different components so that we can provide a full turnkey solutions. One thing that we don't do is Star Tracker because it's really like an expertise by itself, and we prefer to partner with other companies. But I think we are one of the only companies being able to really provide a full ADCS turnkey solutions. Like I don't like to say plug and play because it's never plug and play, but at least it's much easier to parameter and to use than just buying the different components from different vendors and then just expecting that it will magically work together. Um, we are, as I mentioned, working on upgrading our portfolio towards larger satellites. So that means more radiation resilience, um, more passive redundancy. So we are trying to adapt our configuration to, I would say, more demanding customers, more demanding mission scenario. And I think that will be the evolution that you will see with us in the next couple of years. One other aspect that we are trying to cover more and more is interfacing with the propulsion system. So making sure that we do not only provide an attitude control solution, but also an orbital control solution. So we are working with different partners on trying to understand a bit more um, whether we want first to put on our roadmap, for instance, compatibility with electrical propulsion or with chemical propulsion, or so there are so many different propulsion technologies that It's hard to be compatible with every different technology, but so we have to be a bit selective there and identify partners we want to work with and then try to really bring a full solution package all together.
Mm. And is that a very different challenge then, integrating with a propulsion system compared to what you guys are doing now? Is it a whole different product, or is it just fine tuning?
There are some overlap, but it's indeed like a uh, different algorithm, different constraints that you have to take into account.
Hmm.
Um, Even if indeed on the simulation, it's still something that we can do, but making it work, testing it also, testing is a big question mark also sometimes. How do I test my propulsion system with which type of equipment and so on?
Mm.
So
Okay.
that's somewhere we want to go. We are still working on exactly how to tackle that aspect.
Maybe just say a couple of words on actual testing, because obviously conditions in space are very different to those on Earth. Do you do your testing in certain conditions here on Earth before going into space, or do you test up there as
Yes.
well?
So for our hardware in the loop testing, we have an ADCS test bench where it's a air bearing platform. So that's as close as you can be to not having gravity. So you simply, of course, it's like you're able to test on two different axes, and then after you have to turn your satellites and try to simulate that. It's of course never going to be exactly identical to space environments, but you're trying to find some ways to still have representative tests. So we have a solar simulator. We have a cage which is recreating the magnetic field that you are going to experience in low Earth orbit and so on.
Okay. And if a customer comes to you or is interested in purchasing one of your CGMs or something, what's the process? What's the timeline like? What are the things that you need to know from them initially to start working?
So usually we start with evaluating the ADCS requirements. So what kind of mission, the mission size? Is it going to be a communication satellite? Is it going to be a remote sensing satellite? And depending on this, we can make some suggestions of ADCS um, package. Uh, then, of course, it's iterating with the customers on making sure that everything is compatible in terms of interface and so on. And we also usually provide a simulation. So we simulate our customer's mission based on our own ADCS system, so that the customer is able to evaluate the expected performance.
Hmm. Okay.
And if necessary, we can go into more in-depth simulations, but that's something that we would charge at some point. But like the first preliminary discussion is, of course, like something we do for free.
Great. Okay. And just finally, could you maybe give us just one example? You don't have to name company names or anything, but just one example of a mission or a project that you've been involved with, what kind of industry or niche it was in,
Uh,
and some of the details.
yeah, sure. So you were talking about lead time, and so we are able to deliver a full system, like I think that was in less than 6 months from I think we met a customer last August at SmallSat in Salt Lake City in Utah. They told us, okay, we have emissions, we are in a hurry, can you deliver? And we said yes. And so so they had 3U CubeSats launched as a 6U, and they were planning to have them like separate in space and then like demonstrate some technology with them as a tandem, like so some kind of formation flying.
Mm.
Um, and we delivered everything in, I think that was end of November. So that was just 3 months after meeting them, we were able to deliver the full turnkey solution. We were still, of course, working a bit on the algorithm and the software, but we have a support equipment which allows us to upgrade the firmware even after we deliver the hardware. So we're still able to fine tune in parallel. Like the customers are always going to also like tell us, okay, this has changed in our mission, this has changed, and but we are able to upgrade the firmware to take this into consideration, and that has been launched on Transporter 16 last month, I think. Yes.
Nice, very good.
So from first contact to delivery in space, I think they were just like less than 6 months, I think.
Mm,
So
brilliant.
that's, I think, the type of lead time we have to work with sometimes, but also like the level of flexibility we need to have also on our end to accommodate a lot of different customer requirements and make it work.
Sure. Well, good luck in the future as well. Thanks so much, Julien. That was great. Thank you very much for your time.
Yeah, you're welcome.
All done. Thank you.
Thank you. Bye bye.
Bye bye.